Dear students, in previous lecture we discussed continuity of polynomial function and modulus function. Now today we are going to discuss the continuity of some special functions. Now first one is we have to prove the rational functions are continuous. You know that the rational function f of x is equals to px upon qx, where qx is not equals to 0 and px and qx are polynomials. It is the rational definition of the rational function. Now let a be any point of its domain, that is a is the domain of this f, that is this rational function. Now we need to firstly find its limit. Now limit x tends to a f of x equals to limit x tends to a px upon qx. You know that by the algebra of limits, limit of quotient equals to quotient of the limits, that is limit x tends to a p of x upon limit x tends to q a q of x. Now px is polynomial, qx is polynomial, and you know that the qx is not equals to 0 for any point of its domain, which implies that q of a is also not equals to 0. Now here limit x tends to a p of x is simply p of a, because limit of the polynomial is simply the value of the polynomial at that point, that is p of a. Similarly, limit of x tends to a q of x is simply q of a. Also the value of the function, that is value of this rational function at point a, is f of a, which is simply p of a upon q of a. Now here limit exists and the value of the limit equals to p of a upon q of a, which is same as f of a, means the value of the function at this point a. So by definition f is continuous at a. Here a is arbitrary point of its domain, of the domain of this f, which implies that f is continuous at each and every point of its domain. Hence we can say that rational functions are continuous functions. Now the second one is the greatest integer function. You know that the greatest integer function is denoted by f of x equals to greatest integer of x. Now its domain is R, because we can define the greatest integer of each and every real number. Now let a be any non-integer real number, that is if we consider n the nature of this integer, n is integer, this means that this a is greater or equals to n, greater than n, less than n plus 1, that is it is non-integer real number. Now limit of this, firstly we will find limit of this greatest integer function at this non-integer real number. For this we need to find its left and right limit, that is limit x tends to a negative f of x, that is left limit. It is limit h tends to 0 f of a minus h, or we can simply say limit h tends to 0 greatest integer of a minus h. Now a minus h is the number, so it is less than n plus 1 here, because we define this a as n less than a less than n plus 1, which implies that greatest integer of this a minus h is simply n, and limit h tends to 0 and it is constant is simply n. Similarly, right hand limit, that is limit x tends to a positive f of x, is limit h tends to 0 f of a plus h, which is simply f of greatest integer of a plus h. Now greatest integer of a plus h, here a plus h is a number slightly greater than a, and this a is less than n plus 1, which implies that its greatest integer is also n. Hence limit x tends to a f of x is simply n. Also the value of this function at point a is f of a. Now the greatest integer of a is simply n, because a is defined as n less than a less than n plus 1, which implies that the value of the function equals to the limit of the function at point a, where a is non-integer real number. Hence f is continuous at every non-integer real number. Now we will discuss its continuity at integers. If we consider c to be an integer, Then limit x tends to c positive f of x is limit h tends to 0 c plus h. Now c plus h is not integer, it is greater than, slightly greater than integer c, hence its greatest integer is simply c. Similarly, limit x tends to c negative, that is left limit at this point, at point c where c is integer, is limit h tends to 0 c minus h. Now c minus h is a real number. Now it is slightly less than integer c, which implies that its greatest integer is c minus 1, and limit h tends to 0 c minus 1 is c minus 1. Hence from this, clearly limit does not exist when limit does not exist at point c, which implies that f is discontinuous at this integer, hence at each and every integer. So we can simply say that this greatest integer function is discontinuous at integral values, that is at integers it is discontinuous, while as at non-integral values, that is non-integer values or real numbers, this function is continuous. Now third one is the sine function, that is if we consider f of x to be sine x, you know that its domain is R. Now we will check its continuity. Let a be arbitrarily point in the domain of this sine, that is a is the real number, arbitrarily real number. Now limit x tends to a positive f of x, that is right hand limit is limit h tends to 0 f of a plus h. Now f of a plus h is simply sine of a plus h, limit h tends to 0. Now using sine a plus sine b, here it is sine a cos b plus cos a sine b, that is sine a cos h plus cos a sine h. Now putting h equals to 0, it is simply sine a cos 0 plus cos a sine 0, which is simply cos 0 is 1 and sine 0 is 0, so it is simply sine a. Similarly, negative limit, that is left hand limit, is limit x tends to a negative f of x, that is limit h tends to 0 f of a minus h, which is simply sine of a minus h. Using this sine a minus b, we can get sine of a. So this means that right limit is sine a, left limit is sine a, so we can say that limit exists and its value is sine a, that is limit x tends to a f of x is sine a. Similarly, the value of the function, or the value of this sine at point a is simply sine a. So a limit exists and equals to the value of the function at the given point. So f is continuous, means sine is continuous at point a. Here a is arbitrary point in the domain of this f, in the domain of this f or sine, which implies that this is continuous at each and every point. Similarly, you can prove that the remaining trigonometric functions are continuous in the domain, like cos, tan, cot, cosec, sec, etc. The fourth one is the constant function. You know that the constant function is defined by f of x is c, where c is the constant or fixed number. Its domain is R. Let a be the real number, then the left limit is, right limit is limit x tends to a positive f of x is simply limit h tends to 0 f of a plus h. Now a plus h is again c, it is because its value is c, which implies that right limit is c. Also negate this left hand limit, it is f of a minus h, limit h tends to 0, which is simply limit h tends to 0 c, that is c. Hence right limit equals to left limit, right limit equals to left limit, and the value of the function at point a is simply c, because f of a is c, it is constant function, which implies that limit exists and the value equals to the value of the function at point a. So f is continuous at this point a, means constant function is continuous at this point. Now this a is arbitrary point, which implies that it is continuous at each and every point of R, hence it is continuous function. Now the last one is the exponential function. You know that the exponential function is defined by f of x is e raised x or e power x. Its domain is R, because we can define this. Now if we consider a to be a real number, arbitrarily real number, then right limit is limit h tends to 0 f of a plus h, which is limit h tends to 0 e of a plus h, e of a plus h, because by replacing x by a plus h, which is simply e of a. Similarly, negative limit, that is limit x tends to a negative f of x, is limit h tends to 0 f of a minus h, which is limit h tends to 0 e or raised a minus h. Now h is here 0, so it is simply e raised power a. Also, so right limit is ea, left limit is ea, hence limit x tends to a f of x is ea. Also, the value of the function at point a is e raised a. So the value of the function equals to the limit at point a. So by the definition of continuity, f is continuous at point a. Here a is arbitrary point of the domain of this exponential function. So from this we conclude that this exponential is also continuous throughout its domain. So this was all about the continuity of some special functions. So thank you.